for a 74138, which we've already talked about. It's a decoder B multiplexer, right? And what we've done is we've picked up some pins that we call enabled. So y'all are doing labs on enables and disables, right? You'll see how easy that is to do with AND gates and OR gates and NAND gates and OR gates. So they're not going to actually show us, in this one, they don't actually show us the circuitry. Yes, they do. The 74138. So this is what I see. I see this right here. So we got 3 enables on this pin. Well, we got 2 ones they call G2A, G2B, and then they got G1. So G usually stands for gated input or gate. But when you actually look at the schematic, it's nothing but a NOR gate, right? That's serving a negative NAND function. So y'all doing these labs. But what you're going to figure out sooner or later, we're going to have to get away from these internal diagrams, because really all you need to do is understand what the circuit does, and there's really no concern with trying to trace it through. Because if this gate right here goes bad, what do? You replace the whole IC, right? You understand that? We don't do component level, or actually what's inside there. So our component is an integrated circuit. But when we bring up a 7476, which we'll get into later, this is flip-flops, and that was one of our lectures. This is a JK flip-flop. All of a sudden we pick up another little symbol right here. Can y'all see that? So what it is this pin right here has got a triangle on it, and then it's got a bubble. And it's not labeled enable anymore, it's labeled clock. Now, to enable these things, we can do it 2 different ways. We can do it what we call a level triggered. We call it triggered, but it's actually enabled, which would be this right here. So what's this guy looking for? It's looking for a level. It's looking for this to be high. It's looking for this, it's looking for this to be low, this to be low, and this one right here to be what? High. And then it would allow the decoder to work. That makes sense? But when I get over to this guy, this is what we call edge trigger. So anytime when you're looking at a schematic and you see a pin that's got this little triangle on it, that means it's edge trigger or edge enabled. The term we use is trigger. And the bubble means it's triggered on the logo and edge. If I'm going to make something synchronous, I can't synchronize with a level. Y'all understand why? Okay, so I've got a digital pulse. So I've got a string of we'll just put a clock up here. Well, how would I synchronize in something that's that big? How would I synchronize with it? I mean, how would I synchronize with a high when it could be high for a certain amount of time, right? And how can I synchronize with a low if it's going to be low for a certain amount of time? But how many edges do we have? We got 1 edge, or we actually got 2, right? That I could synchronize. I could synchronize on a rising edge, or I could synchronize on a falling edge, because those occur at precise time. Does that make sense? So I guarantee you the microprocessor in here is running, it's a synchronous device, and it's not looking at levels, it's looking at edges. Okay, don't understand that now. So what I need to do is come up with a circuit that detects an edge. I'm listening. That's exactly what this is. Now, this was our lecture. This was in the lecture. According to our rules of Boolean algebra, this would never work. Because we would never, ever, ever get what? Would never, there'd be no way in the world we'd get all highs. So this is why one of the things we said A and with a 0 would always give us a what? A 0. But that's not exactly true. That's ideal. But the problem is, when we do that, we're ignoring the propagation delay of that chip right there. So what happens, when this goes to a 0, it takes a minute amount of time for this to switch to a what? 1. Now, when this goes to a 1, what do I have right now? I have 2 1s because it takes a minute amount of time for this right here to go to a what? 0. So what would happen, every time this went to a 1 on the edge right there, what I would get out of this thing is I'd get a pulse. But I'd only get a pulse on the what? On the rising edges. And we can do this, here we got 1. The problem is I'd have to get my high-speed cut scope. The scope I'm using has only got a bandwidth of 100 megahertz. 25 megahertz. So what I've done is, and it's got to be an odd number of inverters, because if you put an even number, you end up with the same. If you put an odd number, you end up with what? Inversion. So the circuit I've got up here, so we can definitely see this, and I'm using a NAND gate instead of I got a string of 5 of these things hooked up. So that means I got a really nice delay right here that my scope can pick up. So this is the circuit I have hooked up. Well, actually I got 2. Trunks. So this is my edge detection circuit. So I'm getting a pulse out, but notice I'm only getting it on the watt. Here's my input. Here's my signal. Here's my clock coming in here. Yeah, so I'm getting a rousing. Now I'm going to switch this over to an OR gate. And now I get what I'm following. So we can take this little circuit and we can develop a circuit that only sees the edges. Now I can time things, right? So normally anything we say that's synchronous, then it's going to have to time on the edge. Everybody understand that? That makes sense. Yeah, so they don't call it a enable input, they call it a clock input, so it only looks at edges. And what I was saying was, if you're looking at the schematic or the diagram of the device, and you see this right here, you see that triangle, it tells you it's edge triggered. Okay, y'all understand that? And if we see the little bubble, it means it's edge triggered on the falling edge. So that would be this basic circuit that I've got right here. Now, whether you use an OR gate or whether you use an AND gate, all depends on what the circuit is, what the trigger circuit is looking for. So this is an OR gate, and it gives me a negative going pulse. See, my scope's even having a problem. Because we're coming over here and we're looking. Let me trigger on the pulse. So I'm gonna come over here. I'm gonna change it over to channel 2. And then I'll move my trigger up into here. And now we can spread it out. In this scope, it's only a 25 megahertz scope. So we're looking at a pulse. I can see it. We're up at the range of the scope. That's the maximum range of the scope. So we got it on. This is the best we can do, guys. Oh, wrong thing. This is what I'm doing. Maybe I get it here. So we're looking at, this is 25 nanoseconds, so that's about 50 nanoseconds for that pulse. Because I'm going through 5 chips, right? Each one of them gives us, if you don't know what the propagation delay is, for standard TTL, it's about 10 nanoseconds per chip. I mean, per gate, not per chip, per gate. Which works out to be pretty good. So that's 50 nanoseconds. If you took the frequency of that, that'd be 25 times 10 to the minus 6. And we'll take the reciprocal of that. So that's 4 millimeters. That's the pulse of the current. And of course, this guy right here is extremely fast, right? Well, all I wanted to do is just show y'all how we could come up with what we call an edge detect circuit. These are going to be devices that we refer to as edge triggered or level triggered. So if we see E's and we see S's, if we see E's for enabled, they're also called S for strobe. They're also called G for gate. Some of them call them CS for chip select. Well, if you see these, then these are going to be level triggered. They're either going to have a bubble indicating they're low active, or they're going to have not have a bubble that's going to indicate they're low. They're high. If you see this, it indicates it's what? It indicates it's edge triggered. So edge trigger means it's what? It means it's looking for an edge. It's got an edge detect circuit in there looking for an edge. If I come over here and see this, then what it's looking for is looking for the rising edge. Right? You understand? If I come over here and put a bubble on it, then it's looking for a what? A falling. It's not the circuit itself, the edge detect circuit is not complicated. So we see a lot of like counters and stuff like that count on what? On edges. They don't count on levels, they count on edges. So just about all our counters are going to be edge triggered for obvious reasons, right? Because if I'm going to count, I don't want to keep that thing counting up here on the high level. I just want it to count every time I saw an edge come through it. So we'll see when we finally get the counter. So those are edge triggered circuits. Level triggered and edge triggered. Y'all understand the term? So level triggered circuits, these are circuits that enable on a certain level. And then edge triggered means they're only enabled on the edge. Simple little circuit, right? Do so much. But according to what we talked about, we said, okay, if this was a 1, this is going to be a 0, this would be a 1, this would be a 0, this would be a 1, this would be a 0, and the output would be high all the time. When this input went low, the output would be low. So according to our rules of Boolean algebra, this output would be 0 all the time. But we can see for a fact in real life it's not. Because Boolean algebra does not, or the rules of Boolean algebra does not compensate or does not take into consideration the propagation delay of the chip. And what is the propagation delay? Huh? Yeah, it's how long it takes the output to respond to a change in input. That's how long it propagates. The basic gates are not too bad. I mean, a standard gate is like 10 nanoseconds. An LS series is like 9 nanoseconds. An S series is like 3 nanoseconds. But we're talking, we got some of these guys that that can really scream, you know. Yeah, but all we have to do is just use a gate here that has a pretty high propagation delay. And they're building it inside a chip so they can handle that, right? So this scope right here, I wouldn't be able to see one of them because 10 nanoseconds would be beyond the scope of this scope. We got a 100 megahertz scope in there too, but I'm not going to dig it out. So you okay? Okay, we'll start the test about 7 o'clock. So what does that mean? Well, we're going to be in lab until the test.